In this video, I'll talk about how to evaluate in-gram language models. I'll introduce the topic in general and focus primarily on perplexity. I'll show the equation for computing perplexity, followed by a case example to show what it looks like when we work it out. I'll close by mentioning a few potential shortcomings of perplexity that you can look out for if or when you use it to evaluate your own language models. When evaluating language models, there are two different paradigms that you can use. You can go for an extrinsic evaluation, which is where you embed your language model in some kind of downstream application, like, for example, sarcasm detection, and then you compute the differences in task performance when using your language model versus some other alternative. Or you can conduct an intrinsic evaluation, where you measure the quality of your language model independent of any other application. Perplexity is a way to do the latter. It's an intrinsic evaluation metric for language models, and it's basically just the inverse probability of your test set given your current language model normalized by the number of words in the test set. Here's what that equation looks like more formally, letting W be the test set containing words W1 through Wn. So your training set might have 5 sentences, and you'll use the frequencies in those 5 sentences to estimate the maximum likelihoods for your test set, which is maybe another sentence. You'll multiply all of the inverses of the individual in-gram likelihoods with one another, and then you'll take the nth root of that, where n is the number of words in your test set. You'll get a value as a result, and the lower that value is, the better. Thus, if you minimize perplexity, you end up maximizing the test set probability according to your language model. We'll go through an example to see what that looks like. Here we have a small training corpus, so it looks like we have 10 different words in our training corpus, and each of those words happen to occur 10 times. And we also have a test string. Our test string, quite luckily for us, happens to be a string of the exact same words in our training corpus, with each used once. As a refresher, here's the equation for computing perplexity. So we'll go ahead and start working our way through the test string. We're computing perplexity for a unigram language model here, so we'll go ahead and divide the frequency of the word CS by the frequency of all unigrams in the corpus. So that'd be 10 divided by 100 for a probability of 0.1. We'll move on and do this for the next word, 421, and find that its probability is also 0.1. We go all the way through our test string, and since the words all occurred in the training corpus with equal frequency, they end up all having the same maximum likelihood estimates. So now that we have our probabilities for each word, we can go ahead and find the overall perplexity for our test set. For our denominator, we'll multiply 0.1 times 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 0.1. That's counting the probability for each word in our test set. We'll take the inverse of the result, so 1 divided by 0.1 to the 10th power would actually give us like 10 billion. Then we'll take the 10th root of that, and we end up with a perplexity of 10. Now, it's very unlikely that every word is equally likely to occur in the training set, so let's also consider an alternate case where the first 9 words all occurred just one time, and the word Chicago occurred 91 times. If we go through and do maximum likelihood estimates using these counts, we end up with the probabilities you see here. So most words have very low probabilities, but the word Chicago has a very high probability. And then let's take a test string, which is the word Illinois, followed by 9 occurrences of the word Chicago. And this time, when we compute perplexity, we'll have a very small number one time in that denominator, but a very high number 9 other times. This means we end up with a super low perplexity value because it turns out that our test set matches our training distribution really well. We expected to see very few occurrences of other words and a ton of occurrences of Chicago, and that's exactly what we saw. Perplexity can be used to compare the quality of different language models with one another. So for example, if we have 3 different language models and one has a perplexity of 962, one has a perplexity of 170, and one has a perplexity of 109, we might say that the one with a perplexity of 109 is the best language model. However, things like that should be taken with a grain of salt. Improvements in perplexity don't necessarily guarantee improvements in task performance, although the two are often at least correlated. Perplexity is also, in most cases, quite a bit easier to check than downstream task performance, so it's good for quick performance checks during incremental development when it would be silly to do a full task-based evaluation. However, once you have your language model all set up and are ready to run more comprehensive experiments, it's really good to also include an extrinsic evaluation component. Overall, perplexity is a nice, easy metric for performing intrinsic checks on language model quality and can give you a good general idea of how your model performs relative to other alternatives.